Hi guys, welcome to our channel of Sciences and Mathematics. Our topic of discussion for today is going to be a topic under work and energy, and this is going to entail the Gibbs free energy. Now that we have discussed some of the concepts in electrochemistry, and we have said that of course work can be represented in some of the electrochemical processes, of course, which we talked about as redox reactions. And we're going to see in this particular case whereby we're going to use a sample question that this concept of work still continues to be represented in a way. And for today, the concept of Gibbs free energy is going to assist us find out the relationship between the work that we have developed in some of our videos, especially on the concept of electrical work insofar as electrochemistry is concerned. So for that case, thank you and welcome. So as I've said, today we're going to discuss a concept on electrochemistry or electrical work, still which is under the form of energy. And we're going to see that under work and energy, these are the specific topics that we're going to see maybe being discussed in an extensible way, both either in topics in physics and the chemistry, or thermophysics and thermochemistry. So for our topic of discussion for today, this is the Gibbs free energy. Just give this one. So Gibbs free energy comes from the fact that of course energy cannot be free, but this term has been used for this case in a way that we're going to see. But basically it comes from the historical concept of the steam engines. A concept that was advanced by Josiah Willard Gibbs, of course, which we are going to encounter maybe in some of our other videos. So for today, we're just going to limit ourselves to we are going to develop the concept of Gibbs free energy under the electrical work that we had talked about in our previous videos. Our previous video specifically on electrical work in the concept of or in the topic of thermochemistry. So in this case, we talked about redox reactions, and there are some of the reactions which occur under specific conditions, maybe standard temperature and pressure, and there are some others which of course can be able to be initiated using electricity, like the electrolysis that we talked about. And some of these particular reactions, as we are going to see, they're going to entail the concept of maybe specific values for pressure, volume, or temperature. Now in this case, a spontaneous reaction at constant temperature and pressure is accompanied by a decrease in energy. And in this case, this is what we are going to refer to as the concept of Gibbs free energy. So I've talked about the concept of spontaneous reactions. And of course, these are reactions which and this basically refers to reactions or a reaction that favors the formation of products at conditions under which the reactions or the reaction is occurring. So therefore, as we're going to talk about the three conditions that I've mentioned in this, under the Gibbs free energy, we're going to talk about these specific conditions, maybe in case there's need. So in this case, we're going to see that the Gibbs free energy is a negative value of the maximum electrical work. So we're going to represent this Gibbs free energy using the delta G, and by definition the Gibbs free energy is the negative value of maximum electrical work that we have discussed, which is given as QE. So in this case, this basically gives the shorter form of definition of the concept of Gibbs free energy, whereby this is delta G is equals to negative W. So therefore, we had discussed and said that work can be represented, electrical work can be represented as the product of charge times the maximum potential difference, which is represented as QE. But in this case, we have defined Gibbs free energy as the negative value of maximum electrical work. So therefore, we are going to have a relationship between the Gibbs free energy and the electrical work that we have defined by denoting that is a negative value for those particular two set of parameters. So in this case, this also involves the redox reactions that we discussed about. And we saw that for the reaction of iron and copper sulfate, there was the formation of copper plus iron sulfate. So therefore, this entailed a redox reaction whereby, I can just do away with this. Whereby iron was being oxidized whereby copper was being reduced to form that one. This is solid. So therefore, in this case, the first reaction is an oxidation reaction. Oxidation, this is a reduction reaction. If you try to consider these two specific reactions, you can therefore say that in a redox reaction, the number of electrons transferred is going to be related to the quantity of charge that is involved in this specific reaction. So therefore, in some cases, of course, we're going to assign, or maybe in our discussion of oxidation states, we're going to see that ions can have different oxidation states. For instance, for iron, this is iron 2 oxide. This is the green, of course, precipitate that we had talked about, or the green coloring solution that we had talked about. And there's this iron 3, whereby the two ionic states of ions, the one that is there's a variation in color, but of course there's the difference is that the oxidation state for this is +3, while this one is +2. So therefore, we're going to see that the number of electrons that are involved in the formation of these two different ions have a difference of 1. Now, in this case, if we try to take that analogy for the two reactions that we have illustrated, we can see that the number of electrons which are involved in this oxidation reaction are 2, and the same number of electrons are involved in the reduction process. Now, this number of electrons are of significance in a redox reaction, and insofar as the Gibbs energy, free energy is concerned, in that the number of electrons is related to the amount of charge transferred in a redox reaction. So therefore, we're going to give a relationship between this charge that we have talked about and the number of electrons, in a way that the charge on 1 mole of electron, which is called a farad, as a constant number. So for that case, we're going to have a charge on an electron, in 1 mole of an electron, charge on 1 mole of electron. So I presume we understand the concept of a mole from Avogadro's number of particles. So therefore, charge on 1 mole of electron is known as a Faraday. So this is from the work of Michael Faraday. So therefore, it's given the term Faraday, which is given an initial capital F. So therefore, whenever we are trying to mention the concept of the term of a Faraday, it refers to the charge on 1 mole of electron in this particular case. Now this one has got a constant, or a calculated value, which is basically a constant that we are going to mention and probably use in our subsequent discussion for that case. So therefore, 1 Faraday given as 1F is equivalent to 96. It's a large unit, 485 coulombs. So that's the units for measuring charge. So 1 Faraday is equivalent to 96,485 coulombs. Therefore, 1 mole of electron consists of a Faraday, which is equivalent to those number of coulombs. So if n number of moles of electrons are transferred, we can have a relationship between charge and the number of electrons by giving that. So if any number where n represents the number of electrons transferred. So in our case here, it's 2 electrons, then the total charge is going to be 2 times the Faraday that we have listed in that case. So if this one informs one of the aspects of a Gibbs free energy, therefore we can be able to represent N, the product of the number of electrons times the charge, using this particular concept in trying to denote the concept of Gibbs free energy. So if we therefore discussed that Gibbs free energy is the negative value of maximum electrical work, which we are given as negative W. And therefore we discussed from electrical work that we can be able to represent work as a product of charge times the maximum electrical work, which is electromotive force represented by E. And we have said that from a discussion under the concept of a one electron, the number of electrons, 1 mole of electron consisting of 1 Faraday, we can be able to represent Q in forms of the number of moles of electrons times the Faraday. So therefore Q is going to be negative NF E. So therefore the Gibbs free energy will be a value which is a product of the number of moles of electrons times the Faraday times the maximum electrical work, which is EMF. So this is going to form our equation 2. And in that case, therefore, for a reaction that is taking place under standard conditions, we are going to denote Gibbs free energy. So under standard conditions, those are temperature and pressure, we're going to denote Gibbs free energy using that small note, therefore standard, and it's going to be NF E naught. So therefore this is going to give us an equation for representation of Gibbs free energy in terms of the number of electrons, the charge, and the maximum electrical work. The maximum electrical work, which is referred to as electromotive force. So in standard cells, I talked about the concept of a spontaneous reaction, and we said that spontaneous reactions are reactions that favor the formation of products at conditions under which they are occurring. Now that we have subjected this one to the condition of the standard conditions, of course we're going to see that these are just the standard conditions. We're going to see that in electrical cells, which we mentioned as devices which convert chemical energy into electrical energy, when the concept of E standard, which is electromotive force, as a positive value, which I can maybe denote by using positive value, this reaction will be referred to as spontaneous. And then when E is negative or has a negative value, then this reaction is going to be non-spontaneous. Therefore, from the discussion, we're going to see that these specific scenarios are going to be experienced under different conditions in electrochemical cells. And that one, of course, is going to assist us in solve our question, whereby we have a redox reaction for zinc and copper, and we are being requested to calculate the Gibbs free energy under standard conditions, which we have already mentioned and developed from this particular concept. So we're going to see that these two conditions are going to hold in different scenarios, and this is going basically to assist us, our discussion is going to assist us to solve that particular equation. So we can just go ahead and try to find out how we can be able to solve our sample question on the board. So in this case, we're told, consider a reaction below, which is zinc and copper, and then we have E standard being 1.10 volts. Calculate the Gibbs energy in that particular case. So I'm maybe going to quote the Gibbs free energy standard that we have already mentioned in this case, the formula is given on that. So in this case, we are being given E standard, which is 1.10 volts. And we are going to look at the number of electrons being transferred in that redox reaction. The equation is zinc is displacing copper from its ions to form zinc ions, and then plus copper with that potential difference given as 1.1 volts. So this one we can have equations for that, whereby we are going to have 2 electrons involved in that, and then copper gaining 2 electrons to form copper solid. So therefore the number of electrons involved in this specific reaction is going to be 2. So in our information that we have been given, we're going to have also 2 to be the number of electrons. So therefore it's going to be 2. And then the coulombs is going to be the product of F. And now that we have been given F as a constant, which was 96485 coulombs, so 1 F is equivalent to that. Now that we have the information for this as 2F for that one, E for this, therefore we can be able to find the Gibbs, standard Gibbs energy, or Gibbs energy under the standard conditions, by writing this one as negative. So we said it's a negative energy. The negative, we say that Gibbs energy is a negative value of maximum electrical work. So therefore it's going to be negative N 2 times F 96485 times A 1.10 volts. So this is going to give us negative 212 kilojoules. Of course, we said that for the negative value of this this Gibbs energy, for negative value, this reaction is going to be a spontaneous one. Of course, that is for just additional information. Basically, what we were after is trying to find the amount of energy that is involved in this reaction. So for us, we have seen the relationship between work and the Gibbs free energy, the electrical work and the Gibbs free energy, which is a negative value of the maximum electrical work. And this basically are going to be some of the concepts which we are going to see being introduced in our case, whereby the number of electrons is going to be of essence, and then the charge, which is a constant for Faraday, being involved in that case. So basically that's how we're going to handle some of the questions which entail the similar concept under the topic of under the concept of this particular case for Gibbs free energy. And we're guys, bye. God bless.